final part of this workshop is all about molecule search. So molecule search is about traversing the chemical space to identify regions of interest based upon transforming molecules using different construction approaches whilst coupling scoring functions to know which areas of space are desirable and which areas are undesirable. In this particular example, we have taken a lead compound and we will use this in part of a similarity search scoring function, and we will use that to be able to transform an initial fragment, hopefully, into that lead structure. To explore this, we need to use this epsilon-greedy search. So this is the search method that we've implemented. So we can click on epsilon-greedy search, and then we can select all upstream nodes and drag this across to the white space. We can then take the table creator and the fragment, and then we can connect the fragment table to the epsilon-greedy search. Now, usually what we would do is we would actually just go ahead and execute this node. However, instead, what I want to do is I want to double click, and this will actually open the inside of these gray nodes. And these gray nodes are actually called meta nodes. And we can see that we have the DDA workshop nodes open still, but we also have the epsilon-greedy search here. So first of all, what we're going to do is then we're going to go to the recursive loop start. We're going to right click on that, and that will begin then pre-populating some data, and that is actually our fragment. We can then go to recursive loop end, and this is the end of each iteration, and we can press execute. Whilst that's running, we can see multiple nodes are executing, but what we want to do is we just want to right click on recursive loop start. And what we can see here is that we have several molecules being generated. So these are 5 new molecules. And what we'll see is that over time, these numbers will change and these molecules will change. And this is because the search is progressing. And what we want to see is that these Tanimoto scores, so these similarity scores, are improving over successive iterations. So you can see there that the molecules have changed, and so have the Tanimoto similarity scores. So as the search progresses, we will generate more and more data, we'll generate more molecules, but hopefully they will have better overall scores. And again, there you can then see that this has generated slightly better scores, although not as good as we would hope. We would hope that we will get a better jump and we'll be doing a more efficient search. However, in this particular example, we haven't identified any transformations that will yield better intermediate molecules. So just to step through then this sort of search method, how does it work? So first of all, we do a little bit of column renaming. This is to make sure that the data is nice and consistent. Then we go through this molecule construction to generate new molecules. We then have this molecule scoring where we score molecules, and then we choose some molecules to move on to the next loop, which then goes into this sort of recursive loop end and goes back to the beginning recursive loop start. In the molecule construction strategy, I will go ahead and show. It's a little bit more complicated, but what it actually is, it is actually based upon matched molecular pairs of a filtered data set. Now, I can't go through the matched molecular pairs and how they work. However, the key sort of takeaway is that we have built in this particular workflow around 7,700 matched molecular pair transformations, and then we apply them to the new molecules that are coming in. The new molecules are then scored, and in this particular example, we're scoring them based upon a fingerprint strategy using Tanimoto similarity, and we're using, in this particular example, this chemical structure here. Now this is the smile string. I can right click at the top, go to available renders, RDKit 2D depiction, make it bigger, and we can see that this is the actual molecule that we are trying to generate based upon that initial fragment. So I can then go ahead and close. We are also in that particular molecule scoring, we're also doing some deduplication, some duplication checking. And then finally we have this molecule selection phase. This is a little bit complicated again, but this is where we're trying to select the top 5 best scoring molecules and then take those molecules and move on. Because this is epsilon-greedy, what we are doing then is that 5% of the time we actually instead choose 25 molecules at random, and this allows us to have a little bit more stochasticness. It allows us to hopefully get out of parts of the search space that might be local optima. So if we then go ahead and close that, right click on recursion data, then we can see that we've again extended our scores a little bit. So we're now at 0.673 Tanimoto similarity. You can also see that sometimes we actually don't generate molecules that are better than our previous iteration, and this is because it all depends on what transformations are available to us now. So this is molecule search, so it kind of combines molecule construction, it combines molecule scoring, it combines different selection strategies. I just want to show a few other parts of this workflow that is quite nice. So if we close this table now and we then close this, we can right click on epsilon-greedy and we can actually cancel. So one of the things that we can do is we can change the epsilon value. So the epsilon value is how much stochasticity, how often do we want to have randomness introduced into our search. So we can go to, for example, interactive view, slider widget, we can click that. We actually have a slider which we can then change. So for example, instead of 5% of the time, we randomly choose 25 molecules, we can instead change that to instead be, for example, 30% of the time, we randomly choose 25 molecules. We can press apply and then OK, close. The other thing which is interesting is that we could also change, for example, the fragment. So here, the fragment is a fragment which has come through a screen. We explored this fragment a little bit at the beginning of the lecture material, but we could always change this molecule as well. And one way to do this, in fact, is to take the draw the structure node, so in this case it's paracetamol, and we could actually pass this into the workflow, and then we could go ahead and use instead paracetamol to be able to do our transformations. So then we can go ahead and execute the recursive loop start, execute, and instead of using that fragment at the beginning, instead it will use paracetamol, and now instead it will try to transform paracetamol into that lead structure. And we can see that paracetamol is a long way, a large distance away from that final structure. Therefore, we're going to have to run this recursive loop for many iterations. If we want to change the number of iterations that we want to run, I believe that we can go to recursive loop end and we can restart the loop, and we could change it from, for example, instead of 100, we could instead do 10 or 5 or 20. So this is now the end of the sort of foundations for generative design workshop material in terms of the KNIME component. It sort of covers everything at a high level of molecule construction, molecule scoring, and molecule search. In the future, we're looking to do more advanced topics. So for example, how do we build better scoring functions? How do we build MPO, multi-parameter scoring functions? How can we explore different search methods? How could we build in machine learning? However, this gives us a sort of foundation, a flavor of the field. So look out for that in the future. But thank you very much for listening, and I look forward to exploring other topics in generative design with you soon.